Hi Andy, good morning. This is again Dr. C.H. Kiran Kumar dealing you the machine learning part. Today we learn what is called features. Right, next one is feature transformations. What do you mean by feature transformations? Right, feature transformations aim at improving the utility of a feature by removing or changing or adding information. See, future transformations, my dear friends, aim at improving the utility of a feature, useness of a feature. ఒక feature యొక్క utilityని పెంచడానికి we can add by removing some information or changing or adding some information. అలాగ చేస్తే దాన్ని transformation అంటారు. For example, if you have say ఒక 10,000 rows ఉన్నాయి and అన్ని ఒక 20 rows కి మాత్రం చాలా different values ఉన్నాయి, then you just need to remove these 20. అలాగా see this is called feature transformations. Quantitative features are more detailed than ordinal features, followed by categorical features and finally Boolean features. Quantitative features are more detailed, chala detailed ga untayi, so transformations can be applied, followed by ordinal ones and followed by categorical features and finally Boolean features. The transformations are normalization, calibration, discretization, ordering, grouping, unordering, thresholding, and binarization. These are all called the different transformations of feature transformations. Now we talk about each one. Normalization, right? Quantitative kaite anni normalization, calibration, these are all called quantitative versus quantitative. You can have normalization. Quantitative versus ordinal, you have to have, this is called calibration antaru. Quantitative to categorical is called calibration. Quantitative to Boolean is called calibration. Similarly, ordinal to quantitative is called discretization. We'll see what you mean by discretization. Ordinal to ordinal is called ordering. Ordinal to categorical is called ordering. Ordinal to Boolean is also called ordering. Categorical to quantitative is called discretization. Categorical to ordinal is called unordering. And categorical to category is called grouping. Boolean to quantitative is called thresholding and binarization. So these are all different feature transformations. We learn each one by one. What do you mean by normalization of ratings? Means adjusting values measured on different scales to a nationally common scale. That is called normalization. Calibration denotes special types of statistical inference problems. Discretization is the process of transferring continuous functions, models, variables, and equation to discrete counterparts. See, this process usually carried out as a first step towards making them suitable for numerical evaluation and implementation on digital computer. So discretization is very important. Discretization. We will learn all these things in the coming one. Binarization transforms a categorical feature into a set of Boolean features, true or false. Unordering trivially turns an ordinal feature into categorical one by discarding the ordering of a feature value. Unordering. See, thresholding transforms a quantitative or ordinal feature into a Boolean feature by finding its feature split. Right, a simple method that works reasonably well is to choose bins. bins, so that each bin has approximately the same number of instances. Bins. This is referred to as equal frequency discretization. Equal frequency discretization. This is bin 1, bin 2, bin 3, bin 4. So this contains n instances. The second bin contains n instances, something like this. This is called equal frequency discretization. If we choose 2 bins, then this method coincides with the thresholding on the median. That is, if you have only 2 bins, one is true bin, the other one is false bin, that is called Boolean. This is called Boolean. More generally, the bin boundaries are quantiles. Quantiles means 1 by 4. Quantiles, 1 by 4. 1 by 4, my dear friends. 25%, 50%, 75%, and 100%. This is called quantile. Quantile, right? For instance, with 10 bins, the bin boundaries of equal width discretizations are deciles. See, if we divide this with 10 ga divide cheste, that is called deciles antar. Another unsupervised discretization method is equal width discretization. Equal width discretization, which chooses the bin boundaries so that each interval has the same width. Each interval has the same width. 0 to 10, 10 to 20, 20 to 30, 30 to 40. This is called width specification. And the second one is, see here, first 10 values, next 10 values, next 10 values, next 10 values. So this is how discretization principle, right? Switching now to supervised discretization methods, we can distinguish between top-down or divisible discretization method on the one hand and bottom-up agglomerative discretization. See, top-down, top-down, my dear friends. This is called top-down. Top-down, top-down. Bottom-up, leaves first, then internal node, then internal node, then internal node. This is called bottom-up. Bottom-up, this is called top-down. Right. The top-down method is generally called as device discretization method. Device discretization method. On the other hand, bottom-up are called as agglomerative discretization. Agglomerative discretization. Divisive methods work by progressively splitting bins. Progressive. This is called progressive splitting bins. Whereas agglomerative methods proceed by initially assigning each instance to its own bin and successively merging the bins. See, this is split. Find a split. This is how it goes. Splitting bins. For example, if you are to see, for example, if there is a tree, all right, if you want to divide these two, now we just put here Z and we write here A and we write here B. In the same way, this is called splitting. This is called top-down approach, and it is called divisive discretization method. Divisive discretization. And agglomerative and agglomerative means this is how leaves first and then internal. That is called agglomerative. Now, of course, Now top down we use recursion. Top down we use recursion. Bottom approach, right? Now, see, we give an example of each trend. A natural generalization of thresholding leads to top-down recursive partitioning algorithm. Top-down recursive partitioning algorithm. Let us see the algorithm. See, supervised discretization by means of recursive partitioning. Set of labeled instances, yes, ranked on future values f of x, scoring function is q. The sequence of thresholds T1, T2, etc., Tk minus 1. If stopping criterion applies, then return infinite empty. Split S into SL, SL, T, and SR using threshold T that optimizes Q, my dear friends. So, ante threshold ante enti threshold kante mundu unnayonni chinnavi venakala unnayonni peddavi. Now we apply recursively rec part SL comma SL comma F comma Q, and T2 TR is equal to this is called TL rec part SR comma F comma Q. So this is our no. If stopping criterion applied, then return infinite. It is no. How many functions are there here? Because it is applied recursively. Function in the function call. So recursively applied, this criterion will be repeated for a many number of times so that it finally returns T1 union T union TL union T union TR. See, sequence of thresholds. It gives you sequence of thresholds. This is called discretization. Right. So hope you understood, my dear friends. Now, the supervised divisive discretization, we talked about what is called recursive discretization by means of recursive partition. Now coming to aglo merge, here this is merging, and here we use bins. See, set of labeled instances is ranked on feature values, scoring function Q, sequence of thresholds, initialize bins to data points with the same scores. Initialize all bins to data points with the same scores. Merge consecutive pure bins. Kalpesi. See, then you will get this. Evaluate Q on consecutive bin pairs. Merge the pairs with best Q. That best Q is written here. And until no further merges are possible. So this is how it goes. This is called aglo merge. Very simple, my dear friends. Here bins are available. Bins. Take two consecutive round pairs తీసుకోండి, కలిపేసేయండి, ఇలా కలపండి. కలుపుతూ merge the pairs in such a manner that the best Q stopping criteria, the best Q is placed here, something like this. This is called aglo merge. Right, the next two things are normalization and calibration. We already know what do you mean by normalization. Adding a scale to an ordinal or categorical feature. See, is called generally normalization. If this is done in an unsupervised fashion, it is called normalization. Calibration refers to supervised approaches, taking the class labels into consideration. See, normalization means, for example, right, that is called normalization, and calibration refers to supervised approaches. Let us see these. Feature normalization is often required to neutralize the effect of different quantitative features being measured on different scales, that is meters, kilometers, centimeters, something like this. If at all something is there, cm, km, m, so they have to be neutralized. They have to be normalized. That is called normalization. If the features are approximately normally distributed, we can convert them into G-scores, a Z-score or Z-score, by centering on the mean and dividing this mean by standard deviation. Mean by standard deviation. Standard deviation, dividing by the standard deviation. Mu by rho. If we know that the features highest and lowest values as h and I, then we can simply apply the linear scaling. F is equal to F minus L, F minus L by H minus C. Okay, function. We can easily write a function for like F minus L by H minus L. For example, if the feature measures age in years, we may take L as 0 and H as 100. And then we can truncate any F greater than H. H and enta 100. 100 kante peddunte automatically it is truncate to 1. This is called truncation. We know that more than 99% of the probability of mass of normal distribution falls within plus or minus 3 mean, plus or minus 3 rho of the mean, where rho is the standard deviation, plus or minus 3 of the mean, where rho is the standard deviation. So the linear scaling F is equal to F tends to F minus mu by 6 plus half. Removes the need for truncation avasarame undadu. This removes the truncation. F is equal to F minus mu by 6 standard deviation. 6 plus half. This is called no need of truncation. Now, what do you mean by feature calibration? Feature calibration is understood as a supervised feature transformation, adding a meaningful scale carrying class information to arbitrary features. This has a number of important advantages. For instance, it allows models that require scale, such as linear classifiers, to handle categorical and ordinal features. It also allows the linear algorithm, learning algorithm, to choose whether to treat features as categorical, ordinal, or quantitative. The problem of feature calibration can thus be stated as a feature F extends to F. Construct a calibrated feature FC. Calibrated feature FC is tends to x to 0, 1, such that FC of x estimates the probability of FC of x is equal to P of positive such that V, where V is f of x. Probability of positive by f of x is the value of the original feature of x. So this is the calibration. some form. For categorical features, this is as straightforward as collecting relative frequencies from a training set. This is called calibration, normalization and calibration. And there is another feature called as logistic feature calibration. Logistic feature calibration. Estimate the class means mu positive and mu minus mu negative and the standard deviation rho. Transform f of x into z scores, g scores, making sure to use mu is equal to positives plus negatives by 2 as the feature mean, Rescore g scores to fd, where d is dimension, d is fdx is equal to d dash into zx, where d dash is equal to mu positive minus mu negative by standard deviation, mu positive minus mu negative by standard deviation. Apply a sigmoidal transformation to f for d of x to give calibrated probabilities like fc of x is equal to exponent of f dx by 1 plus f dx. This is called logistic feature calibration, my dear friends. Logistic feature calibration. Another one is isotonic calibration. Isotonic calibration, a method that requires order but ignores scale. Order is important, ignores scale, and can be applied to both ordinal and quantitative features. We essentially use this feature as univariate ranker and construct its ROC curve and convex hull to obtain a piecewise constant calibration map. This isotonic calibration, a method, requires order but ignores scale. This is mainly used for ROC curve and calibration map. Suppose we have an ROC curve and suppose that ith segment of the curve involves Ni training examples out of which Mi are positives, Ni training examples out of which Mi are positives. The corresponding ROC segment has a slope Li is equal to Mi by C into Ni minus Mi, where C is the prior odds. So this is called isotonic calibration. Isotonic calibration. Isotonic calibration. That's it. Right. Similarly, isotonic feature calibration performs the following steps. Sort the training instances and feature value. So first sort cheyali such that ROC curve has AUC, area under curve, is greater than or equal to 1 by 2. Area under curve is greater than or equal to 1 by 2. Construct the convex hull of this curve and count the number of positives Mi and the total number of instants Ni in each segment of the convex hull. Discrete the features to the convex hull segments. Associate calibrated feature value VCI. VCI is equal to Mi plus 1 by Mi plus 1 C into Ni minus Mi plus 1 with each segment. If an additive scale is required, use VDI is equal to log of VCI by 1 minus VCI. This can be written as log of VCI minus log of 1 minus VCI. So this is the end of, all right, what is the last one is incomplete feature. Incomplete feature. Missing feature values at training time are trickier to handle. First of all, the very fact that feature value is missing may be correlated with the target variable. For example, the range of medical tests carried out on a patient is likely to depend on the medical history. For such features, it may be best to have a designated missing value so that, for instance, a tree model can split on it. However, this would not work for, say, a linear model. In such cases, we can complete the feature by filling in the missing values. This process is known as imputation. No imputation. ఎలా fill చేస్తావు? The missing values are filled with either no by average తో fill చేస్తావు or median తో fill చేస్తావు. For instance, in a classification problem, we can calculate the per class means. Per class means medians or modes over the observed values of the feature and use this to impute the missing value. This is how it is. A somewhat more sophisticated method takes features correlation into account by building a predictive model for each incomplete feature and uses that model to predict the missing value. See, missing values, incomplete features are, see, very, very important and in a project. First, this is called, so this is the first phase which we do in any ML project. ML project law, this is the first task we will be doing. Right, missing values are to be identified. Next, the last one is future construction and selection. What do you mean by construction? What do you mean by selection? Construction అంటే ఏంటి? For example, ఒక feature ఉంది, దానిని ఆర్ రెండు ఫీచర్స్ ని కలిపి ఒక ఫీచర్ గా కన్స్ట్రక్ట్ చేయటం, లేదా ఒక ఫీచర్ నే n ఫీచర్స్ గా డివైడ్ చేయటం. వీటన్నిటిని what we say is future construction. And selection is based, no, if you have 29 features, no, do you want to consider all these 29 features into consideration, or you want to go with only some features? That is called selection. You can write it on your own. In the information retrieval literature, a multi-word phrase is referred to as n-gram, unigram, bigram, trigram, and so on. We can construct a new feature from two Boolean or categorical features by forming their Cartesian product. For example, shape with values circle, triangle, and square. And another feature, color, with values red, green, blue. We can then create a product would be the feature shape, color is a feature with values circle red, circle green, circle blue, triangle red, triangle blue, triangle green. Similarly, like square, something like that. So, ee vidhanga kuda manam feature construct cheyochu. We can take arithmetic or polynomial combinations of quantitative features. First, apply concept learning or subgroup discovery, and then use these concepts or subgroups as new Boolean features. Boolean features means no, either yes or no, either true or false. This is called feature construction. And feature selection. What do you mean by feature selection? Once we have constructed a new feature, it's a good idea to select from the subset. See, filter approach. This approach scores features on a particular metric, and the top scoring features are selected. That is called filter. Relief feature selection is a method which repeatedly sample as random instance X and finds it nearest hit. Random ga apply chestadi, nearest hit H తీసుకుంటుంది, as well as its nearest miss M. And the ith features score is then decreased by distance of xi comma hi whole square and increased by xi comma mi whole square. That is, okay, hit aithe then the score is decreased by distance of xi comma hi whole square. Hit aithe, miss aithe then decreased, miss aithe it is increased by, the score is increased by distance of xi comma mi whole square, where d is some distance measure. So this is the method by which relief feature selection method. This is called relief feature selection method, and this is called filter. Filter ఏంటంటే ఏదో ఒక మెట్రిక్ తీసుకుంటుంది, టాప్ స్కోరింగ్ ఫీచర్స్ ఆర్ సెలెక్టెడ్. As simple as this. This is called selection of features. Now, wrapper is another approach to select features. Wrapper. The idea is that feature selection is wrapped in a search process that usually involve training and evaluating a model itself. Now, forward selection methods start with an empty set of features and add features to the set of one at a time as long as they improve the performance of the model. See, ఒక్కొక్కటి తీసుకుంటాం, ఒకటి అసలు ఏం లేవు, add one feature F1, do the same, find the performance of the model, then F1 comma F2, now find the performance of the model, and then F1 F2 F3, find the performance of the model. This is how it goes. Backward elimination starts with full set of features and aimed at improving the performance by removing features one at a time. See, idemo add one at a time, idemo remove one at a time. See, most approaches apply a greedy search algorithm that never reconsiders the choice it makes. So this is wrapper approach. Now, future construction and selection from a geometric perspective, assuming quantitative features. Here, matrices are used to represent the features. See, a data set as a matrix X with n data points, in rows n data points and d features. D features, n rows, which we want to transfer into a new matrix W with n rows and r columns, n by r. We assume that X is zero-centered. So W is equal to XT for some D by R transformation matrix T. For example, feature scaling corresponding to T by a D by D diagonal matrix. D by D diagonal matrix. This is called diagonal matrix, and can be used feature selection by removing some of these columns. The rotation is achieved by T being orthogonal. T dash is equal to I. Clearly, several